Okay, so today's tutorial is just going to be relating t-statistics to p-values. So it's going to allow you to see by the end of these 5 minutes how having a t-statistic relates to that p-value or the sig value that you get in your SPSS outputs. So to start with, let's just do a recap of a hypothesis test. Here we've got our standard normal distribution. This is bowl-shaped and symmetric, and it's got a mean of 0. Okay, and what we're going to do is we're going to look at a two-tail test example. So that means that if you were trying to find a critical value, you'd be using the column in your tables where alpha is equal to 0.025. And we're also going to assume that we've got a big sample, which means that what we're going to be doing is, hopefully it's one of those numbers that is stuck in your mind by now from when we've done enough of these t-tests. We need to find a critical value for a large sample. The critical value is going to be plus or minus 1.96 for a two-tailed test. So let's just put those on our graph. So we can see that in the negative region we've got a critical value of minus 1.96 and a similar of 1.96 in the positive region. Okay, and now we're going to firstly just do a recap by looking at how this type of graph, this distribution, relates to t-statistics that you might get from your coefficients tables. So let's take the example of something that is significant, first of all, and that's going to be income. So here the dependent variable is your demand for bicycles, and what we're finding is that our income might be an important explanatory variable. We get a t-statistic of 5.253. How did we get that? Well, actually all we did was we divided our coefficient term, beta, by the standard error, which is given there. Okay? And if you've been in my seminar groups, the way I've explained this is we now put our t-statistic on this graph. Here it is, 5.25, and imagine we start at the middle. In order to test whether we reject the null hypothesis and have statistical evidence that this is an important explanatory variable, we just want to know whether it can get far enough to jump over this dashed line here. And yes, in this example, we see that it can jump over the line and therefore it passes the test. What you would write then, as we did in our seminar groups, is that we can reject the null hypothesis and we've got evidence that income is an important explanatory variable in determining our demand for bikes. We can also take an example like the price of bikes, and here our t-statistic is minus 0.795. Again, we found that by dividing our coefficient by its standard error. And in this time, again, we start at the middle. It's a negative number, so we're going to move to the left. All we want to know is if this sits far enough on the scale that we can jump over the line. And in this case, we see that it doesn't quite get there, and therefore it doesn't pass the test. In this case, we would review that we cannot reject the null hypothesis, and we do not have statistically significant evidence that the prices of bikes influences their demand for bikes. Okay? But the important thing for today is trying to relate those numbers, our t-statistics that we got here, to the sig values or p-values that we get otherwise. So we've got just the same thing as we started with. But what we need to realize is that what a p-value is asking is, what is the chance that we could have got a more extreme value for our t-statistic than the one we actually achieved? Okay? And essentially what we're therefore saying is, what's the probability, the p, the chance, that it's going to be either in this region here, which forms 2.5% of the distribution, or this region here, which again is another 2.5%, because we're looking at the 95% significance. These two tails add up to the extremes together of 5%, and this main bulk is the 95%. Because we don't care whether it's here or here, we add them together, so what we're asking is whether p is less than 0.05. And we can put this on another scale that sits just below our distribution graph. And essentially, this 0.05 that is related to the one here is just the same as being in line with the 1.96 that we've got there. The reason I've put it this way round, we shall see in a second. Let's go back to that original significant variable of income. And the sig value here was 0.000. So that's a little bit like lying here. And so to try and use the same idea, it's like, imagine you start on this side of the scale, and what we're asking is the p-value or sig value small enough that as we move from left to right, does it manage to jump past this 0.05 element? Okay, and in this case, because just as our t-statistic could jump across this line, we see that our sig value can jump past this line, and it's smaller than 0.05. Therefore, we know that we've got a significant variable. It's jumped across. And again, we can also use the example on the price of bikes. But here, this time, notice that the sig value is 0.430. Again, imagine we start at this end and we're seeing if we can jump past this 0.05 threshold. We see that we don't quite get there. Okay? Because 0.430 is a bigger number than 0.05. And therefore, this one doesn't pass the significance test. Just in the same way as the fact that minus 0.795 doesn't quite get past minus 1.9. A couple of things to remember. We were doing an example of a two-tail test. If you're going to do a one-tail test, you've got to halve the sig value in order to do the same type of evaluation. So in this case, this number should be instead 0.215 instead of 0.43. The main point to take away, or for you to remember, is that a big t-statistic will create a small p-value or a small sig value. And if the t-statistic is big enough to jump over the line on the distribution graph, it means that the sig value or the p-value is small enough to jump over the 0.05 line. Okay? We looked at the example with a 5% significance, and that was when p had to be less than 0.05, so it had to get below that. If we wanted an even more accurate example, we could look at the 1% significance level. Okay, and that would be the column in your table that's 0.0005. And in that case, p has got to be smaller than 0.01. It's got to get even further to the left-hand side. Or we could have a more weaker strain. We could look at the 10% significance level. That's the 0.05 column on your tables, and in that case p has got to be smaller than 0.1, so it hasn't got quite so far to travel. Okay, so you might well find that some of these sig values pass the tests for this level, but maybe not for this level. So that was everything I wanted to go through today. I hope that makes it a little bit clearer, the relationship between t-statistics and p-values. And that's one more thing you can tick off in your revision.